Hey, this is Leach with Simpson Math, and in this video, we're going to be talking about Pascal's triangle. Now, Pascal's triangle is one of my favorite little mathematical quirks. There's so many interesting kind of things that you can kind of discover with it. And if you're in my contemporary class, towards the end of your homework, you'll go through some exercises that will take you through some of those interesting special things. Now, the Pascal's triangle is really nice because in terms of how we're using it in our contemporary class, is that it's a way to be able to visualize the combinations, the NCR. And previously, I've mentioned how the NCR is a special case to counting orders when we have two groups of indistinguishable objects, like a success and a fail. In a little bit, I'll be talking about how Plinko, like the Price is Right pricing game, Plinko, that follows this kind of pattern as well, where success might be, or our two indistinguishable groups could be like going to the left or going to the right, the little chip going to the left or to the right. So if your entire situation, if you have n number of things and all of them can be divided into basically a binary situation, an on or an off, a left or a right, a success or a fail, then you can use combinations, the combinatorics formula to actually kind of count the orders. All right. So we've talked about it previously. Let's take a look at Pascal's triangle and how it's made. Now, if you look on what my Pascal's triangle, this is what I refer to as the Legend of Pascalda. If you're familiar with the Legend of Zelda games, there's a thing in the game called the Triforce that pops up a lot. It's a source of power, also wisdom and courage. And so that's what the colorization of it. One interesting thing about Pascal's triangle is if you well, I'll talk about how this is built in a second, but if you look at some of these, if I've highlighted the even numbers, if you highlight the even numbers, an interesting kind of pattern arises. And if you make Pascal's triangle even bigger and keep going, this pattern kind of keeps going. And it's technically a fractal. As you get this bigger, this pattern of triangles within triangles keeps showing up. And the person who first discovered that is Sierpinski, and so I've nicknamed this the Sierpinski Triforce. I do have a little bit of swag and merch, like this sticker. That this object here is a sticker, which I have right here. I have my the enamel pin that kind of started all this. My husband and I, we have a little enamel pin sticker business. Basically, we have certain designs we want to be enamel pins, so we get them printed. But when you get them made, you have to have like 100 or so made. So we get them made and then sell the rest. And then also do have it put onto a t-shirt, as you can see on my camera or on the screen here. So how is this thing made? So we kind of start with up here at row 0. We have this 1, and you can imagine that there might be kind of zeros above here. But the general process is you like taking a look at this 3, you can add up the 2 diagonals to get it made. Then you add up the next 2 diagonals, add up the next diagonal, so forth. So if I'm making this from scratch, I'll put a 1 in the center of the page. You can kind of imagine there's zeros over here, and we're going to add the diagonals, and we get a 1 and a 1. I want to add up the diagonals with these kind of imaginary zeros that are here. And then keep adding that up. So this kind of, understood 0 that's there adds up with that 1 to be 1. 1 plus 1 is 2. 1 plus 0 is 1. Keep going. And you can see like here, 1 plus 4 is 5. 4 plus 6 is 10, so forth. So we just keep that process filtering down. And like I said, this thing keeps going forever and ever, but it does start getting pretty big pretty quickly. Here we are at row 15. And row 15, notice we're at already at like towards the center here to like 6,000. The next one would be in the 12,000s. So it gets pretty big pretty fast. When we're numbering these things, this top row is row 0. Then we have row 1, row 2. And then the columns, notice how the row 5 here has 6 numbers in it. Because this first one is actually row 0, or kind of column 0. Then we have 1, 2, 3, 4, 5. In terms of combinatorics, in terms of the combination formula, the NCR, this, like for example, this 5 right here would be 5, choose 1. This 10 would be 5, choose 2. This other 10 would be 5, choose 3. We've talked about previously how There's some symmetry you might be noticing. Like we had a question in a previous video where it was a situation where things were kind of split in two, and the question was like, well, how many ways could you have? It was like maybe three successes and two failures or something, and it didn't matter whether you put into the three, put in the three, or put in the two, you got 10 because it's just kind of about a point of view. There is a notable amount of symmetry here. Um, so they follow that combinations because it is a special case of these two groups of indistinguishable objects. And I'm going to use kind of Plinko to help us out here. So Plinko is one of the Price is Right pricing games. This particular image was taken from like a primetime special when it was 100,000 in the center. If you've ever watched this, Drew Carey makes a big deal that 10,000 is in the middle because mathematically, as long as there's no weird physics, I think those Plinko chips might have a little bit of spring action in them or something, or the pegs kind of might wiggle a little bit because it will sometimes kind of shoot through a whole bunch of them at once. But in theory, if a chip hits a peg and has a 50-50 chance to go on either side, then hits another peg, 50-50 chance to bounce, you want to drop it in the middle because you will end up with, on average, hitting that number in the middle. Now, Price is Right knows what they're doing, and they put the zeros, which are also rather common, right beside the big jackpot because it makes for good TV. And then they also then give away less money. In theory, like we see here, I've done the math here on how to figure this out. So if you take a look at these numbers, you start seeing Pascal's triangle show up here. So when a chip hits this first peg, there's only, if you're dropping it dead center, there's only one way to for one path for that chip to go. Like I said, it could go 50-50 on either side. And so now there's, if you look at the total here, there's a total of two, a sum of two on this row, and one of them is to the left, and one of them is to the right. Then 50-50 again on either way, bouncing. Notice there's now a total of four possible paths that could be taken to get to those chips, and to get to those pegs. Again, we're assuming we're just dropping from the center. So there could be one way here, two ways here from it following this path and this path, and then just one way here. So let me kind of jot, so if you're looking at these numbers, we have 1, 2, 4. This sums up to 8. This next one will sum up to 16. If we keep adding these sums, you should notice something that's special about these horizontal rows is that they are adding up to 2 to the 0, 2 to the first, 2 to the second, 2 to the third. And for what we know about our set notation, about set stuff, that is the total kind of, if you remember, if I said I have 6 objects, how many different subsets could there be? It would be 2 to the 6th. It's following under kind of a similar kind of counting process here as well. That's interesting. So if we look at this row here, this third row 3, like there's 3 total ways to get here. So 3 ways to get here. So it's I'm going to the left twice, once to the right, going to the left once. Left. Oh, let me start over. It is in total left 2 times, right once. But notice we're kind of in the order of these. Remember that we can only do with order with combinations when it's 2 groups like this, 2 yeses and nos, but it is technically like an order. 2 lefts and a right. 2 lefts and a right. We have 2 lefts and a right. It just happens that we go left, right, left, and this one is right, left, left. So in order to get to that particular spot, we have 2 lefts and a right, or 2 failures and a success. I just find that's interesting that it does follow this. This red stuff was my calculating and figuring out the different possible ways, because this particular one, if I hit this peg, it'll hit that wall and then come back. So it kind of, the Pascal's triangle does kind of break down a little bit there. So I just find that interesting, this initial application of the Pascal's triangle that you'll be seeing throughout this is a way that instead of doing the combination formula, like I said, if you wanted to find 5, choose 2, you can just look in the Pascal's triangle and grab that. In my next video, we're going to be seeing how we can do the binomial expansion, and then you can just grab that whole row without having to do the 5, choose 1, 5, choose 2, 5, choose 3. You just have the triangle. You can just grab the row. So it's just a nice little way to build out all those combinations. It does run into a problem because it gets pretty big pretty quick. So obviously, if you're going to do combinations of anything kind of remotely bigger than maybe 10 or 11, then just, definitely use use your calculator for that. All right, just wanted to just give you a little bit of a overview of the Pascal's triangle, how it's built, some interesting kind of relationships. There's way more cool observations about the Pascal triangle than what I've covered here. And if you like Legend of Zelda and you like math, SimpsonMath.com has, or Simpson Math on Etsy, Simpson_math on Etsy, has these pins, stickers, and shirts. All right, you have a good one. I'll see you in the next one. Bye.